Today we have Bradley Hauer, who will be talking about lexical semantics, why theory matters. So Bradley Hauer is a PhD candidate at the University of Alberta. He's published more than 20 papers in refereed venues. His work covers a variety of subjects in natural language processing, including multilingual semantics, classical decipherment, and cognate identification. His present research is motivated by a strong interest in theoretical models and explainable methods. So very excited for this talk. So Bradley, floor is yours.
Thank you very much for that introduction. So yes, I am Bradley Hauer from right here at the University of Alberta, Department of Computing Science, and today I am going to be talking about why theory matters in lexical semantics. Now, one of the standard textbooks in natural language processing was written by Daniel Jurafsky and James Martin, and in the most recent edition of that textbook, they describe lexical semantics as the linguistic study of word meaning. So the overall setting in which we find ourselves for today's talk, what we're talking about when we say lexical semantics, is designing automated systems that have some awareness of what words mean when they process text. So that could include things like translation systems, word sense disambiguation systems, or WSD, and we're going to be coming back to that task quite a bit through this talk, question answering, information extraction. Those all fall within the heading of lexical semantics, which in turn is part of natural language processing, which is NLP, which itself is a subfield of artificial intelligence. So artificially intelligent systems that work with human languages, we say that's natural language processing. Within that, we have all these different tasks that require some awareness of word meaning. For example, if we want to answer questions that a human agent has, then of course we need to have some idea of what the words in that question mean so that we know which information the human is looking for. And all of that contributes to this flagship goal of natural language understanding. The idea of trying to build systems, automated systems, that have some internal model of language that allows them to understand what's going on and make inferences and carry out tasks based on that understanding. Now, one of the foremost researchers in lexical semantics is Dr. Roberto Navigli. And in a 2018 paper, he said the following: natural language understanding aims to make sense of language by enabling computers to read and comprehend text. The key question is, therefore, how to derive meaning from natural language by overcoming its inherent complexities. And it is this making sense of, this idea of wanting to understand what is working, what phenomena and what relations between those phenomena are actually at work when these semantic models are deployed. What are they actually modeling? And what are the phenomena that we can see from linguistics that are actually enabling these models to do what they do? And so it's that making sense of that is motivating the work that you will see in this talk today. And the reason that I find that so important, so interesting, and so vital to lexical semantics and natural language processing in general is that modern natural language processing tends to exhibit a very strong focus on maximizing performance on benchmarks. So having some standard suite of benchmark data sets, some standard tasks, and trying to get the highest accuracy or the highest F-score or the highest precision, or have a model that can run in the lowest amount of time. And these are all worthwhile goals. Of course, we want our systems to be as accurate as possible and as efficient as possible. But the issue that we have is that these pre-trained neural language models that have taken NLP by storm in the past several years, models such as BERT, BART, Roberta, those are names that you're probably familiar with if you have been following recent work in natural language processing. These models tend to give good results, but they are very difficult to explain. These models are constructed in such a way that they are very opaque to analysis. And this is very important because, for example, if one of these models makes an error, if it gives the incorrect output, it can actually be very difficult to understand why that is, what went wrong. And this has given rise to an area of research that I've seen referred to as Bertology, obviously using BERT as a representative of this class of models, where the idea is just trying to figure out what exactly these models are actually doing. So just trying to explain these models. And so what I'm going to be talking about today is why theory matters and why this focus on maximizing performance at the expense of interpretability is actually creating a real gap in the literature. Specifically, my position is that computational lexical semantics suffers from a lack of human readable theory. Proponents of neural language models will often say, and I think they have a point, that the model is itself learning some kind of theory of language, that it is learning some way of representing various linguistic phenomena and leveraging them to solve semantic tasks. But this theory is not generally available to humans. It's not something that we can easily interpret. And so the three questions that I would like to provide some insight into today, and that I hope you'll have some insight into by the end of this talk, is first, how can we analyze semantic tasks? How can we take these tasks that are used to evaluate semantic models, and how can we think about those tasks and how they relate to one another? Second, what linguistic phenomena can we make better use of? What are we not explicitly or perhaps even implicitly utilizing for lexical semantics that might allow us to achieve better results? And finally, where can this be applied? How can this actually be deployed in practice to improve performance on tasks? So how can we establish that this is actually of practical as well as theoretical value? So those questions, I hope, will lay the foundation for proving this central thesis of why theory matters. So this will be a talk in three parts, each covering a line of research that I've done as part of my thesis work here in the department. And so the first of those three parts is titled WIC equals TSV equals WSD on the equivalence of three semantic tasks. And this was presented earlier this month. So this is actually very fresh research at the conference of the North American Association for Computational Linguistics. So the outline for this section is that we're going to be talking about three tasks that are used to evaluate systems in lexical semantics: word sense disambiguation, or WSD, the word in context task, or WIC, and the target sense verification task, or TSV. And the central hypothesis that is underlying our analysis of these tasks is that sense is equal to meaning. That is, all three of these tasks have some dependence on human judgments relating to sense or meaning. And our hypothesis is that two words in context are judged to have the same meaning if and only if they can be annotated correctly with the same sense from some predefined discrete sense inventory. We will argue in favor of this hypothesis by showing that there is equivalences, by formulating reductions between these tasks to argue that they are equivalent to one another. We will then validate these reductions empirically by actually implementing the reductions and showing that we can solve WSD instances with a WIC system, or vice versa, thereby showing that if you have a system to solve one of these problems, you can solve any of the others. And finally, we will conclude this part of the presentation by making the case for WordNet as an important resource in semantics and as the standard sense inventory for these tasks. So first is this word sense disambiguation, or WSD task, that I've alluded to a few times. And this is a flagship task in lexical semantics. It is very well researched. It has been the subject of study in computational linguistics for decades. And the task is to identify the sense of a word in context. So for example, if a system is given the sense, I could hear the bat flapping its wings, we would want it to be able to identify that that is referring to a flying mammal rather than a club for hitting a ball. Now, of course, if we're going to talk about a system selecting a sense of a word, we need some way of enumerating the possible senses. We need some way of giving the system a list of possible senses which it may choose from. And the de facto standard for that in the literature is WordNet. So WordNet is a resource that was actually developed in order to test certain theories in psycholinguistics, testing theories about how humans represent language psychologically. However, it has since found widespread usage in computational linguistics as a resource for semantics. So how WordNet was constructed is it takes words which lexicalize the same concept and puts them in a set of synonyms, or a synset, a synonym set. So you can see here we have this context. You haven't got the heart for baseball. And using our linguistic intuition, we can say that we can replace heart here with nerve. So you haven't got the nerve for baseball. Or perhaps metal. You haven't got the metal for baseball. So in this context, all three of these words can lexicalize the same underlying concept. They are synonyms. They can substitute for one another in this context. And so WordNet has a synset which contains these words, and that synset will correspond to the concept that is being lexicalized in this sentence here. So this concept that is expressed by nerve or heart or metal corresponds to this synset which contains the words that can lexicalize it. You can see WordNet assigns an 8-digit identifier to each synset it contains, and that can just be used to uniquely refer to it. It's a bit of an unwieldy system, but it does work. So in that, from that view, a sense just becomes a pair of a word and a synset that it contains. So we can enumerate the senses of a word by looking at the synsets that contain it, or equivalently, looking at the set of concepts that it can lexicalize. And of course, under this system, a word can have any number of senses. It can belong to a single synset, or it can belong to 20 synsets. So a word can have any number of senses under this system. Now, the second task, oddly enough, does not depend explicitly on a sense inventory at all. So it's a departure from the word sense disambiguation framework. And indeed, this was one of the motivations for the proposal for this task back in 2019. So word in context, or WIC, is a binary classification task where we ask, does the target word have the same meaning in two different contexts? So we have here the example, the board has 7 members, and he got out the board and set up the pieces. So in this case, if we give these sentences to our WIC system, we would expect it to say that no, the meaning is clearly different across these two sentences. The word does not have the same meaning in these contexts. And the final task that we'll be looking at in this part of the talk is target sense verification, or TSV. This is a task that is relatively recent, having been proposed just last year. It is also a binary classification task, where we ask the system the question, does the target word in a given context have a given sense? So if the context is the sentence that you can see here, the trailer for that movie is fun to watch, and the sense is what you see right here in this picture, a transport conveyance pulled by a truck. Well, that's quite clearly not what trailer means in the context provided. There it was referring to an advertisement for a movie. So we would want our system to return a negative classification in this task as well. This sense is not the sense of this word in context. Now, our hypothesis is based on the observation that all three tasks depend on judgments about word meanings, either relative to one another or relative to some sense, either a list of senses from a sense inventory or a single given sense, as in the case of TSV. And our hypothesis, to elaborate on what I said earlier, is that different instances of a word have the same meaning if and only if they have the same sense. So this human judgment of meaning, we hypothesize in our work, lines up with the sense inventory that we discussed earlier. And we say that it follows from this that these three tasks are equal. WIC equals TSV equals WSD. So despite the different formulations of these tasks, they are in fact equivalent to one another. And the argument here is an argument from reduction. So let's suppose we have a WSD system. We don't need to know how it works. All we know is that it solves WSD instances. And let's suppose we're given an instance of the WIC task. So we have two contexts, C1 and C2, and a word that appears in both of those contexts. And we want to ask, well, how can we solve this with our WSD system? Well, we just solve the WSD instance corresponding to each of those contexts. So we assign a sense to W in the first context, we assign a sense to W in the second context, we check if they are equal. If they are, then under our hypothesis, since they have the same sense, they should have the same meaning, and vice versa. Now, suppose we're not actually given a WSD system. Suppose we are instead given a TSV system. Fine. How can we solve WSD instances with TSV? We're given a context and a word, a WSD instance, and we need to determine the sense. Well, using WordNet, we can enumerate the senses of the word. Again, look at the synsets that contain it. And for each of those, we construct a TSV instance. We just ask our TSV system, is this the sense, S1? How about S2? Is S3 the sense? And so on. So I only have 3 examples here in this diagram, but of course, in practice, this could scale to any number of senses. We work under the assumption that a word in context has precisely one correct sense. Therefore, there should be exactly one instance that returns true, and that should correspond to the sense of the word W in the context C. Now, let's suppose we don't have a TSV system, but we do have a WIC system. How can we solve a TSV instance using WIC? That is, how can we reduce TSV to WIC? Well, we're given a context, C, a word W, which appears in that context, and a sense S. And we want to know, is S the sense of W in C? So we use a simple method of generating an example for S. So we generate a context in which W does have sense S, and we just ask our WIC system, does W have the same meaning in the example of sense S as it does in C? And if they have the same meaning, well, if they have the same sense rather, then they should have the same meaning. So our WIC instance should be true and obviously false otherwise. And so what we have here is a cycle of reductions. If we have a WSD system, we can solve WIC. If we have a TSV system, we can solve WSD. And if we have a WIC system, we can solve TSV. So what we've shown is that a solution to any of these problems gives a solution to all of the other 3. Let's take a look at some examples to make this a bit more concrete. Let's take this WIC instance here that we looked at earlier. The board has 7 members. He got out the board and set up the pieces. How can we reduce this to an instance of WSD? Well, we just take each sentence on its own. We apply a WSD system, and we get out the senses. So this is just another way of representing WordNet senses. So this is the first synset in which the noun board appears. This is the 9th. So board has quite a few senses in WordNet. But we can clearly see that the sense assigned to board in the first context is not the same as the sense assigned to board in the second context. So because they have the same sense, under our hypothesis, they must not have the same meaning. And so our WIC output is negative under our reduction. Now let's assume we have a WSD instance, and let's see if we can solve it with WIC. So working our way around the cycle of reductions to solve a WSD instance with a WIC system. I could hear the bat flapping its wings. So this is the example we saw earlier. So we generate examples for each possible sense of bat. So bat in this context means a club for hitting a ball. Bat in this context means a nocturnal winged mammal. So we have forced the word bat to explicitly have the sense that we want to test in each context. And here our WIC system, if it is functioning correctly, will say that no, these 2 usages of the word bat do not have the same meaning, negative. But here in this case, they do have the same meaning, positive. So we say, okay, that must be our correct sense. This first sense, referring to a winged mammal, that is going to be our WSD output. So now that we have made this theoretical argument, how can we validate it empirically? How can we argue that this actually works in practice? So our reductions all depend on this sense meaning hypothesis, and we're going to test the 2 reduction directions exemplified on the previous slide. We're going to test reducing WSD to WIC and vice versa. Now, of course, there is no such thing as a perfectly accurate WSD system or WIC system. And so what we want to look for here is not how good is the accuracy. Our goal here is not to propose some state-of-the-art method for solving either task, but rather to ask, is there evidence against our hypothesis? Does this empirical validation support or refute the hypothesis that we are advancing. And so the specific systems we use is Escher for WSD and Liori for WIC. So these are very strong systems, both of which were published in the literature last year. And so we're going to use those to fill in those WSD and WIC boxes respectively. So let's look at the first, solving WSD with WIC, so testing that reduction. We use the Semi-Val 2007 WSD dataset. Given a WSD instance, we generate an example for each sense, as we saw in the examples. We apply a WIC system to the context and to each example, and we return the sense with the highest score. Now, based on an analysis of the performance of the system and the average number of WIC instances that we have to generate, we expect an accuracy of about 34%. So relatively low as WSD systems go, but remember, our goal here is not to be state-of-the-art. Our goal is to test whether our hypothesis is true. And under our hypothesis, we expect an accuracy of 34%. What we actually observe in practice is an accuracy of 48%, so substantially higher than what we actually predicted. So we interpret that as strong evidence for our hypothesis. The reductions work as our hypothesis says it will. In fact, they work a bit better. Let's go in the other direction. So we use the WIC dataset from the Semi-Val 2021 shared task. Given a WIC instance, we apply a WSD system to the target word in each context. If the WSD system assigns the same sense to each instance, we return true, otherwise false. Again, based on a theoretical analysis, we expect to see an accuracy of about 78%, just based on how accurate our WSD system is. And in practice, we observe very close to that, actually slightly higher, at 79%. So again, we interpret this as very strong evidence for our hypothesis. We're getting almost exactly the result that our hypothesis would predict. So I want to wrap up this part of the talk by just making the argument for the continued use of WordNet. Sense inventories are crucial to semantic annotation. If we want to have sense annotated corpora, which are vital to tasks such as WSD and can indirectly be useful for tasks such as machine translation, we need some way of annotating words in context. Moreover, we find that WIC annotations tend to agree with WordNet sense distinctions, exactly as our hypothesis predicts. So our recommendation based on these findings is the adoption of WordNet as the standard sense inventory for the WIC task. And we also argue, as we will show later in this talk, that WordNet has strong practical and theoretical advantages. So wrapping up this part of the talk, we have demonstrated the equivalence of WSD and WIC by way of TSV. Our experimental results and the analysis thereof confirm our sense meaning hypothesis. This is a surprising finding, which follows from the WordNet properties, which are vital to semantics research, and we hope that our findings will stimulate future work on these tasks. So that leads into the second part of my talk today, on the universality of lexical concepts. So this is also work that, like the first part, was a collaborative effort between myself and my supervisor, Dr. Greg Kondrak, and this was presented late last year at the SIGTIP conference. So lexical semantics, to reiterate, is the linguistic study of word meaning. And what motivates this part of my talk is, as I said, this increasing emphasis on engineering versus science, in semantics in particular and in NLP in general. We have these models that can do very well, but it's very difficult to explain what underlying linguistic phenomena are actually driving them. And so based on that, I see a need for a theory-driven understanding of the idea of concepts, senses, synonymy, and translation that are so crucial to the study of lexical semantics, and also the need to have clearly stated assumptions and inferences relating these phenomena to one another. So in other words, we need to understand the phenomena we are working with in order to explain our results. That is a vital part of the science of lexical semantics. Now, this is an elaboration on the figure that we saw earlier, introducing WordNet, but now we're taking it beyond the monolingual setting. So we're no longer working with just English. You can see that now in this example, I've added French and Polish examples as well. So within a language, we have this phenomena of synonymy, this idea that one word can substitute for another without changing the meaning of the context in which the word is embedded in particular contexts. So we see again that phenomena of mutual substitutability or synonymy gives rise to synsets. And analogously, the phenomena of translation, so the idea that in this context, we could translate heart as one of these French words or one of these Polish words. Those words can express the same concept in their respective languages. That gives rise to multi-synsets, multilingual synsets. So we can see here a synset from BabelNet, and you can see that's indicated by the BN synset identifier, that contains not only words that can substitute for one another within a language, that is to say, synonyms, but they also contain translations of one another. So words that can express the same concept within or across languages. And just as this gives rise to senses in the monolingual setting, so too does it allow us to enumerate the senses and translations of senses in multilingual settings. Now, multi-word nets have seen widespread usage in lexical semantics for the reason principally that they work. And I would like to take a moment to talk about why I believe these multi-word nets work so well, why they've shown such great results over the past decade or so in lexical semantics. And I believe the chief reason for that is that they are grounded in real intuitive linguistic phenomena, synonymy and translation. So you can see here in this example, under the bridge on the bank of the river, each of the content words in this sentence corresponds to some lexicalizable concept, so some BabelNet synset. And from that, we can choose a translation of that into another language, which we can see here. So these BabelNet synsets, these lexicalizable concepts, serve as a sort of interlingua, where every word corresponds, is lexicalizing one of those concepts, and this is preserved across the translation process. This is a prerequisite for a literal translation. Now, a common criticism of the WordNet model is that it leads to relatively high granularity. That is, we have a lot of senses that are very similar to one another. And while I acknowledge, having worked with these resources extensively, that this level of granularity can be inconvenient, it is necessary to maintain this property of semantic equivalence within multilingual synsets. And this is because translation can depend on very subtle distinctions of meaning. So sometimes even those very fine-grained distinctions can matter when translating from one language to another. So the takeaway from this is our proposal for the idea of concept universality, the theory of concept universality. So let's start at the top here. We have this concept of fruit, the concept lexicalized in English as fruit. And we can see in French and Polish and Chinese, there are various ways of lexicalizing that concept, but the concept itself remains fixed. And likewise, there are these concepts of apple and banana, each of which can be lexicalized by words in various different languages. But there is intuitively a relation between these concepts. An apple is a fruit. A banana is a fruit. So this is the is-a relationship or hyponymy. Apple is a hyponym of fruit, banana is a hyponym of fruit. And this holds regardless of which language we work in. So any of these words here, any of these translations for apple, in its respective language, under our theory, will be something of this type. This hyponym relationship holds independent of the language that we are working in, and that is because the concepts are the same. We have different ways of lexicalizing them in different languages, but the concepts themselves are universal, and so too are the relations between them. So what are the implications of concept universality? Well, first, it tells us that these multi-word nets that I discussed, multilingual word nets, that they are modular, that we can add and connect new languages, new words, and new concepts, and all of it is going to fit into this universal structure connecting these lexicalizable concepts with various relations. And because of this, because the concepts and their structure are language independent, that means that we can build these multi-word nets without necessarily having to worry about any bias toward high resource languages such as English. For example, we do not need to worry that the conceptual structure of English will dominate these resources necessarily, because that structure is actually universal. So while bias may exist, it need not exist. And finally, multi-word nets based on this model, as I alluded to earlier, have already proven extremely useful in natural language processing. So for example, BabelNet. And my proposition is that as we come to understand these resources, these multi-word nets, as we develop a better understanding of how they work, we will be able to do even better. We will be able to improve these resources and improve how they are used in order to achieve still better results. So that leads very nicely into the third and final part of my talk, semi-supervised and unsupervised sense annotation via translations. So this is joint work, again, not only between myself and my supervisor, but also with two other students in our group and another professor in this department. And this is work that was presented at RANLP, Recent Advances in Natural Language Processing, last year. So we're going to return now to this task of word sense disambiguation. And in particular, we're going to try to classify WSD systems. So I want to present to you this diagram on the right-hand side of your screen that is showing various different WSD systems. So eWiser, eWise, UKB, Mulan, Eurosense. These are all different systems for doing WSD. And I've classified them along two perpendicular axes. So first, it's the question of whether or not the WSD system requires sense annotations. Does it require some training data, some examples where WSD has already been done in order to learn a model to do further WSD? If it is, we say that it is supervised, or alternatively, as we'll see in this section of the talk, we can say that it is semi-supervised if the training data is in a different language than the system than the data that it will be applied to. So for example, if we were to train a model on English, or if we were to depend more generally on English training data, but then we test on French, let's say, that would be semi-supervised, because even though it is dependent on training data, the training data is in a different language than the language that we ultimately want to do WSD on. Now, the alternative to that on the vertical axis is systems that do not require sense annotations. So we say that these are unsupervised or knowledge-based systems that do not need any examples of WSD to learn from. Now, on the other axis, the horizontal axis, we have traditional WSD versus corpus tagging. Traditional WSD is the standard formulation of the WSD task, where we are given a set of instances, a word in a particular context, and it is expected that our system will disambiguate all of them. So we want to annotate all the words and be as accurate as possible in that annotation. The second possibility is corpus tagging, and that's what we're looking at in this part of my talk. Corpus tagging is when the goal, you are not given some fixed set of instances, rather you're given a corpus, a large body of text that is not sense annotated, and you want to annotate enough words to train a WSD model to maximize precision. So this can be seen as tying in to the supervised and semi-supervised systems, because if we can do corpus tagging, then the goal is to actually generate training data that can be used as a set of examples to learn a supervised or semi-supervised model that can then go on to do WSD on its own. So again, the task that we're looking at is automatic corpus tagging, where we want to produce a sense annotated corpus suitable for training a WSD system. Again, we need not annotate every word in the corpus. And the key idea that we're leveraging in this work is that a word's translation provides information about its sense. So again, this is building on top of that idea of concept universality, that literal translations should lexicalize the same concept. They express the same concept. And so we believe that we can leverage that to improve what we can do with automatic corpus tagging systems. And so the questions are, the questions that differentiate the three methods that we propose are: what assumptions can we make, And how can we mitigate the effects of noise within the system? How can we maximize precision so that we're minimizing the amount of noise that we're passing to the WSD system trained on the data that we produce? I'll do a brief overview of some of the resources. BabelNet, I've already introduced, and we're going to be talking about that as a method of sense translation mapping. So given the translation of a word, what are the possible senses that it could be translating? We're going to be using Babeline to align words within sentences, allowing us to identify the translation of a particular word. And that's based on work that was published 2 years ago. Actually, this came from our group. Issei Luan, the first author, is a former master's student within our research group. UKB, alongside SyntagNet, is an unsupervised WSD system, so it requires no training data. And we're going to be using that as part of some of our approaches. And so that was proposed in 2014 and then expanded with SyntagNet in 2019. And finally, from the same paper as Babeline, we're going to be using the soft constraint method, which is a way of revising WSD based on translation information. So if WSD has already been done and we have the translations of the text, so we have senses and we have translations, soft constraint actually allows us to revise those annotations, to try and correct them, to increase the precision. So let's look at the first of our 3 methods of generating training data for WSD. This is going to be a semi-supervised model. So we're assuming that we have some sense annotated corpus in some language, which we'll call our L1. So we have a sense annotated corpus in L1, but what we want is sense annotated data in L2. So L1, for example, could be English, where we already have quite a few sense annotated corpora available. And sense 2 could, for example, be, let's say, Polish, which doesn't have as many sense annotated corpora available. So we want to generate additional data to train our WSD systems. And so the idea here is to first translate the L1 corpus. Then we apply some filtering steps, both of which depend on Babeline. We use a translation filter and an embedding filter. And that's on the sense annotations that we project across the alignment. So we align the corpus with its translation, and operating under the concept universality assumption, the concept universality theory, we assume that a word in the L1 and the L2 word with which it is aligned, its translation, have the same sense, the same concept. So then once we have those annotations, in order to correct for noise, either noise in the translation or noise in the original corpus, we apply 2 filtering steps, the translation filter and the embedding filter, and that ultimately leaves us with a tagged L2 corpus, which is a translation of the L1 corpus that retains a subset of the annotations from the original corpus. So that's our first method, which we call label prop, because it is propagating the labels from the original text to its translation. The second of our 2 methods is what we call label sync. So this is an unsupervised approach. So now we don't assume that we have any sense annotated data in any language. We need to generate all of our sense annotations purely from scratch. So what we do is we start with a bytext, which is a text that is translated into at least one other language. So we have the L1 side of the bytext and the L2 side of the bytext, with each side being a translation of the other. So we have the same text in 2 languages. That's a bytext. We do unsupervised WSD on both sides of the bytext using UKB along with SyntagNet. So again, this is an unsupervised WSD system. It doesn't need any training data, so it's perfectly fair to use that in the unsupervised setting. And that's making use of both SyntagNet and BabelNet. And that sense tags the corpora on both sides. But of course, because UKB is an unsupervised system, we expect its output to be actually quite noisy relative to what we would want for our training data. So we apply the soft constraint approach using the translation information to refine the annotations that UKB produces. And then again, we apply a translation-based filtering step. And so the end result of label sync is 2 sense annotated corpora, 1 in each of our languages. So this could be applied theoretically to any bytext in any pair of languages to generate a sense annotated corpora for both. The final method is label gen. So here, the method is asymmetric. So in the previous approach, in label sync, we did not give special treatment to any language. We did not make any assumptions about what L1 and L2 are. Here, we're actually assuming that one side of our bytext is English. And this is because we observe in practice that since most systems are developed for English and since more resources tend to be available for English WSD performance is typically higher, particularly in the case of UKB. So what we do is we annotate the English side of the English to target language, the English to L2 bytext using UKB, and then we essentially follow the label prop method. We treat the sense annotations on the English side as though they're a kind of gold standard and just apply label props. So we propagate those sense annotations across the alignment links onto the non-English side. We apply the soft constraint approach to refine those annotations. We apply the same filtering steps as we did for label prop, and that results in a corpus in the non-English language that is sense annotated and that can be used to train a WSD model in that language. So now we come to the evaluation step. So in order to evaluate one of these corpora, what we're going to do is actually train a supervised WSD system using the corpus that our methods produce. And if our methods are working properly, then we should get better results than competing corpus annotations methods. So we're going to use two supervised WSD systems, IMS, which is now over a decade old, but is still used for validating training sets in WSD, and an MBERT system proposed in 2020 by Barba et al. So the idea is that we will take the corpora produced by our systems and we'll take the corpora produced by competing systems. We will train IMS models and MBERT models for each of them, and we will see which yields better performance. So first, let's look at the results in the semi-supervised setting. So this is on the Semi-Val 2013 and Semi-Val 2015 multilingual WSD datasets. So these are aggregating over experience in French, Spanish, Italian, and German, I believe. And our primary competitor here is Mulan. Mulan is the previous state of the art for semi-supervised corpus tagging. And you can see here, just looking at the red bars, when we train IMS on the data produced by our semi-supervised method, label prop, the result is better performance. IMS actually does better than when you train it on the Mulan data. And likewise, when you fine-tune MBERT using the corpus produced by label prop, you get better results than when you train, or rather when you fine-tune MBERT on the data that Mulan produces. Both of these methods outperform the most common sense baseline. So we are outperforming that on this data set. And we are also able to outperform when we fine-tune MBERT using the data that we produce using label prop. We're also able to outperform the Aries and zero-shot methods from prior work. So you can read more about those traditional WSD methods in our paper. But fundamentally, we are able to outperform not only the previous state-of-the-art for corpus generation, but also for some traditional semi-supervised WSD systems as well. Let's move on to the unsupervised setting. So here we, once again, are going to fine-tune MBERT using the data produced by our unsupervised methods, label sync and label gen, and compare them to models trained using the data produced by OneSec, which is the previous state-of-the-art for unsupervised corpus tagging. And you can see, once again, that when MBERT is fine-tuned on our data produced by either label sync or, better still, label gen, the results are better than what we see compared to when MBERT is trained on, or sorry, when MBERT is fine-tuned on data produced using OneSec. And again, with the label gen method, we are actually able to outperform some traditional WSD systems. Finally, looking at the English results. So we've previously looked at multilingual results, but now we're going to focus on English, specifically the benchmark, the standard WSD benchmark provided by Raganato et al. 2017. And what we're going to compare to is not only OneSec, which again is the previous state-of-the-art for unsupervised corpus tagging, we're also going to compare to models trained on SemCore. Now, SemCore is a supervised model. And we say that it is supervised because SEMCOR itself is actually a manually disambiguated corpus. It was disambiguated not by some automated system, such as OneSec or LabelSync. It was actually disambiguated by people. So we expect it to have a much higher quality. Nevertheless, when IMS is trained on the data that LabelSync produces, the results are not only higher than what we observe compared to when IMS is trained on OneSec's data, it is actually higher than what we see when IMS is trained on SEMCOR. So you can actually, when using IMS, you can actually see that the data that we generate with LabelSync is actually better than what you would get with a fully supervised model. Now, we don't see that with MBERT, only with IMS. However, again, even when MBERT is our WSD system of choice, our data still yields better results than OneSec. So wrapping up this part of the talk, we have presented 3 novel, scalable methods that can generate WSD training data, leveraging recent advances in machine translation, alignment, and contextual embeddings. I have shown you that we are able to achieve state-of-the-art results on multiple languages, including some unsupervised results rivaling those of supervised models. And we make not only our code for our systems, but also the corpora that we generate available to facilitate further research. So that brings us to the end of my talk. So I just want to briefly summarize our contributions. In the first part, I showed you some analysis of 3 important semantic tasks that have been proposed and researched independently, but which I have argued are equivalent to one another. I have introduced our theory of concept universality, which leads to a theory of multilingual semantics that allows us to tie together these ideas of sense, synonymy, and translation. And finally, in the third part, I talked about new methods and resources for WSD that shows that we can take these ideas of multilingual lexical semantics from theory to practice. If you are interested in our work and would like to talk to us or perhaps work with us, my email address, bmhauer@ualberta.ca, and my supervisor's email address, gkondrak@ualberta.ca, are both at the bottom of the screen, and we would love to hear from you. Thank you very much for your attention. I would be happy to take any questions you have.
Hello, can I ask questions?
Sure, of course.
Yeah, thanks. Yeah, I'm Lily Mo, so from the department. So yeah, thank you very much for the talk. And I especially like the first part, which is pretty deductive. You have some hypothesis, and then you kind of evaluate it in the, in empirical results to justify the hypothesis. And you also mentioned, there are a lot of Bertology research, which we don't really understand. So there's another trend in the literature that not only Bertology, but people are proposing, various esoteric tasks. You don't really know what the task is about, but they just publish more papers by creating new tasks, new settings, new data sets. And now you show that some of the tasks are really equivalent. And indeed, some of the tasks are newly proposed, like in 2021, and it's equivalent to previous work. Does your work suggest that we should, take a, put less efforts in proposing those esoteric tasks, but address on more real stuff? What is the semantics? What is how can we really capture the meanings, not just doing one more, more and more tasks, and people do more and more benchmark, models and achieve higher performance?
Right. So thank you for the excellent question. And that's an insight that I also share and that I have also observed. But I don't think the 2 goals that you gave are mutually exclusive to one another. I'm not against people proposing new tasks. In fact, I think that can be a very good way of stimulating research and interest in these kinds of models and in these phenomena. However, what I would advocate for is that we should think more closely about what these tasks are actually doing, and think about, is this task really just a different formulation of something that has already been proposed? Is it equivalent to or reducible to an existing task? In theoretical computing science, people talk a lot about hierarchies of hardness. Is this task reducible to this one? Is it as hard as this one? And so what I would like is to see more of that in NLP, to see more of thinking about, is this task no harder than this task? Or is this task perhaps strictly harder than this task? For example, can we prove that you can have a reduction in one direction, but not in another? So I think rather than just proposing these tasks just because they're new, I think we should think a lot more closely about what the underlying linguistic phenomena are and what kind of understanding the system would actually have in order to be able to solve that task.
Yeah, thank you. This is great insight, and I quite agree with that. And also, I mean, from a practical point of view, we also need to think of what kind of application it supports. Some of the papers we are publishing, not we are publishing, but people are publishing are really toyish stuff that we don't really know what they're about.
Yes. Yeah, thank you very much for your question.
So if anyone has other questions, please feel free to unmute yourselves and ask Bradley directly.
Also, I cannot see the chat while I am screen sharing. So if there is a question in the chat, if someone could please just read it out to me.
I'm monitoring the chat. So.
Okay, fantastic. Thank you.
Are there any other questions?
Okay, can I ask more questions? So
Sure.
I think one of your hypotheses in the first part was meaning is semantics. So is meaning a synonym of semantics? Is there any difference when we say meaning and semantics, and why you say, a word has the same meaning means it has the same semantics?
Right. So this is the perennial problem of definitions. So if you define something, then you have to define every word that you use in the definition. Then you have to define every word that you use in those definitions. And sooner or later, you run out of words. So the approach that I typically take is that I view meaning as something atomic. Meaning is just this essential idea that if you and I are talking, as we are now, you have some idea of what I mean, and I have some idea of what you mean, and we're able to convey this meaning back and forth to one another using words as containers for our ideas. And so that's what I mean by meaning is the ability to understand what another person is saying and how that relates to concepts, to lexicalizable concepts, be they abstract or concrete. So in terms of distinguishing meaning from semantics, I would say that semantics, as far as the study, as far as it in the sense of lexical semantics, I would say that semantics is awareness of meaning. Semantics is about the ability to know what meaning is and to know what it means for two things to have the same meaning and to study that and be able to apply that in research. So again, it's necessarily very vague, because if I give a definition of meaning, then that sort of just kicks the can down the road, and then we have to talk about what words I use to define meaning. So like I said, it is tempting to just say that meaning is this atomic concept that we know that we are able to exchange with one another through speech or through text or through writing, and that's what we are trying to understand when we do semantics. Okay, does that make sense?
Yeah, sure. Of course, I mean, we do the definition. At some moment, it will be loopy, or at some moment, it will be atomic. Some concepts cannot be defined. But then the hypothesis was not really needed in inducing your theorem, because you can just treat semantics as an atomic concept, and then the hypothesis is not needed. You can still derive all the theorems, the two equivalents.
I would disagree with that, because the hypothesis I stated is not relating semantics to meaning, it's relating senses to meaning. Okay. So we're talking about that if we have this discrete sense inventory, if we have a WordNet, and I say, what is the meaning of this sense in this context? Or sorry, what is the meaning, or what is the sense of this word in this context? And what is the sense of this word in this other context? Then the hypothesis is that if and only if those words can be assigned the same sense, the same synset from WordNet.
So, sorry, I messed up my question. So what's the difference between sense and meaning?
Right. So the difference between sense and meaning is that sense is inherently discrete. So when we're talking about a sense inventory, we're
Okay.
talking about a discrete representation of the concepts which a word can refer to.
I see. The meaning is more vague. It can be, any, anything that you want to convey, and the word is the container, as you mentioned, to convey the meaning. Then you say that the word has the same sense if and only if they have the same meaning.
Well, that's something that is sort of the contrary to my hypothesis. My hypothesis is that contrary to what you very often see in vector semantics, for example, I don't think meaning is necessarily discrete. We know, so what my hypothesis is establishing, just taking a brief step back, is that we know sense is discrete. We have these discrete sense inventories. We've been using them for decades. We know that they work, that they have real applications. And the question is meaning also discrete? Is meaning this very continuous thing where one meaning just sort of fades into another gradually on some kind of continuum? Or is meaning, like sense, also discrete? So when we ask a human annotator, does this word have the same meaning in these two contexts? Is that a continuous phenomena or a discrete phenomena? And under my hypothesis, since sense is equal to meaning, since sense is discrete, under my hypothesis, meaning is also discrete. So that's what I'm arguing in that part of the presentation.
Maybe I could ask a question. I'm not a linguist, so but I do work with language in a kind of a different way, and that is that I'm interested in getting computers to do things, right? So I want to be able to talk to a computer, and I want to be able to get it to do something. And so what's important to me when I is not so much whether or not the meaning maps to something, but whether or not the computer can do the thing that I want it to do, right? And so in that sense, meaning has sort of infinite variation, because in any context, the meaning is very much related to whether or not the computer can figure out, sorry about that, should figure out or can figure out what I'm talking about, and then respond to my functionality. And so there's an infinite number of things that a computer can do. And so in that sense, there's an infinite number of meanings, because you look at a sentence, I can change some part of the sentence in a very subtle way. And from what does that word mean in that context, the computer can decide to do something very, very different than, so this is sort of, so there's like this sort of infinite, so I guess, have you thought much about sort of like understanding meaning in terms of what we want computers to do versus understanding meaning in terms of versus meaning that, say, a linguist would ascribe to some word when a linguist analyzes the word? And I think that those are functionally very different kinds of things.
Excellent point. So I'll address this as best I can, because I think it's a very broad, almost philosophical issue, but I'll try to address it as best I can, which is to say that, in the third part of my talk, I did make the case for how these discrete models can be used to solve important tasks. So WSD could have practical use cases. For example, if you're using an electronic reading device, and you ask, what does this word mean? You might have someone who is learning a language and perhaps doesn't know what a particular word means, or perhaps you simply encounter a rare esoteric word and you need to look up the meaning of it. It would be very helpful if, rather than just presenting a list of possible definitions, as many electronic devices do today, if the system could select a sense from a predefined sense inventory, such as WordNet, and tell you, in this context, this word means this. And so we can think, going back to what you said about infinite possible variations, there's an infinite number of possible texts that I could be reading on my digital device. There's an infinite number of books people could write, infinite number of articles, infinite number of every kind of text that I could be reading. But fundamentally, what I want the computer to do in that case is to tell me, in terms of some discrete sense inventory, what does this word mean? What does eclectic mean in this particular context? What does hyperbole mean in this particular context? So ultimately, even though there is infinite possible variation, as you say, I would say that does not preclude us being able to actualize that by having the machine work with some discrete linguistic phenomenon. Does that?
No, I think that that's a really good point. I mean, so one use. So what you're talking about really, in some sense, is explainability, right? I mean, if I'm asking for, like, I can think of another application of that idea, and that is the computer did something, and I'm trying to figure out, I wanted to explain why it did that thing based on what I told it to do. So the only, there's an infinite. So I think that there's an infinite, sense of, there's an infinite number of, concepts out there, if you like, and that the meaning of a word in some context is completely, functionalized, if you like, by all of the other words around it, right? And so it's functionalized by all of that. So its specific use is determined by all this context, but nevertheless, you still wanted to be able to discreetly tell you, hey, this is what I meant. This is what I thought you meant, right? Or this is what I meant when I was doing that thing. And that has to be some kind of clear concept in concept space. And so I think that what you're saying, yeah, makes a lot of sense. Or, so if I look at a word and I want to look it up in a dictionary, or I want a dictionary kind of definition, I can't have an infinitely large dictionary, right? So making it discrete makes it more useful in that sense.
Yes, I think that's a really excellent point. And just sort of adding on to that, as part of this discussion, you referred to this knowing why a system does what it does. And that's something that is a very big issue with these neural models, where you can have these very deep neural models that can have huge numbers of parameters. And so your model might make some mistake. For example, when I was working with Escher and Liori for these experiments in the first part of the presentation, I would often find these systems making mistakes when I thought the answer was completely obvious. I thought, well, how could the system possibly get this wrong? But there's really no way for the model to tell me, well, I outputted this answer because of this. All you can really say is, well, when these matrices are multiplied by these vectors,
yeah, exactly.
This number is bigger than this number by 1.63. So that's the output the softmax classifier gives you.
That makes sense. Yeah.
And so this idea of explainability, you use the word explainability, and I use that myself. I believe I actually used it in this presentation, and if I didn't, then I should have. But explainability is absolutely crucial to these models, because if we don't know why they're making mistakes, then it's going to be very, very difficult to fix them.
Yeah, absolutely.
Excuse me, may I just jump in?
Sure.
So just the point about what Bruce here said, because I worked on a project related to this concept universality principle in Greg's course. So the idea of having an infinite number of senses or meanings, well, I think this is totally true, but the point is that actually what we are interested in WSD is not really all those nuances in meanings. So again, the idea of granularity is important here. So all we want to do in an NLP task, for example, in a WSD task, is to distinguish the two obviously different senses of, for example, the word bank, one of which being, well, the financial institution, the other one being the riverside. So here, all those nuances which lead to an infinite number of senses do not really matter. So if we see this task as having the right level of granularity, then we wouldn't really care about those infinite number of senses that are well, we know there are present, but they are not something that we are interested in to work on. And that's what makes this concept universality principle work in WSD tasks. But it might not sound very attractive to a linguist, because a linguist is aware that, okay, we have infinite number of senses for a word.
Well, I'm not sure a lexicographer would agree with that. Part of linguistics is lexicography, which is enumerating the possible senses of a word. For example, if you open up the Oxford Dictionary and you go to a particular word, you'll see an enumeration of its senses. So I think from a linguistic perspective, I'm not sure that a linguist would agree with this idea of infinite possible senses. Certainly, dictionaries are not infinite, as Bruce alluded to earlier. Certainly, WordNet is not infinite. BabelNet is not infinite. Yet I do not think that necessarily means that any concept has to be missing from it.
Yes, but when you have different dictionaries considering different numbers of senses for the same word, then it's actually an indication that, okay, different people can have different understandings of the senses for the same word. So yeah.
Well, another thing,
and even if when dictionaries do not list all those infinite senses, it does not mean that they do not believe that they exist. But again, they believe that for any practical reason, listing, I don't know, the 5-10 most common senses would be enough. But that does not necessarily mean that they do not believe in infinite number of senses.
So I think what this comes down to is the notion of granularity. How fine-grained do our senses need to be? And under the WordNet model and the BabelNet model, I would argue that the level of granularity we need is exactly the level of granularity that maintains semantic equivalence within multilingual synsets. So as long as I maintain this property that within a language, I can substitute a word for a particular concept, and across languages, I can translate a word, I think that's the level of granularity that is the correct level of granularity, because that's the one that speaks to these underlying linguistic phenomena of sense, synonymy, and translation.
Exactly. Determining that level of granularity, I think, is essential, and that makes something either work or not work. Yeah, exactly.
Yeah, but I think that there's sort of a deeper idea, though, right? And that is that, for explainability, this is useful. For lexical analysis, for itemizing things, this is all useful. But again, my argument again is for getting computers to do things that we want them to do. I think that a deeper theory that addresses the the infinite nature of meaning is more important. And I'll give you another example that's really interesting to think about, right? And that is, let's say you ask a computer to draw you a picture of a bear. So I've been playing around with DALL-E now. It's really quite an amazing tool. If you get it, you can try it. But if you say, draw me a bear, every time you get it to draw you a bear, it's going to draw a completely different bear. Right. So there's an infinite number of bears that it can draw. What made it think of that bear versus that bear? Right. And the reason there's an infinite number of bears that it draws is because there's an infinite number of ideas of what bear means. And so again, if I want to get a computer to draw the exact same bear, like I tell DALL-E draw bear, and now I wanted to draw the exact same bear. How do I do that, right? How do I even get it to do something similar? What technique can I use linguistically to describe, two bear pictures that are going to be identical? How's that even possible? So if you just think about itemizing the words, and if you just think about translation, then things kind of start to look discrete. But if you start trying to get computers to do things that are human-like, then you need a deeper theory.
Fantastic point. So I think what we're driving toward here is this distinction between senses and named entities. So let's take another example. If I ask DALL-E to draw me a building, and then I ask it again, draw me a building, it'll draw two different buildings. But if I ask it, draw CSIS on the University of Alberta campus, or draw the engineering building, or draw the administration building, or draw Hub Mall on the University of Alberta campus, or draw me the Alberta legislature, because those refer to specific instantiations of a concept, they're not concept, they're instantiations of a concept, it should be able to draw me the same building. If I tell DALL-E, draw me the Eiffel Tower, and then I say again, draw me the Eiffel Tower, if the system is working correctly, it should draw the same building for me. And that's because I've given a name to a specific instantiation of the concept of building. So we have this concept of building.
Bradley, there is also variation in this, so it can draw it from different perspectives.
That's true. That's an excellent point.
It's infinite, and not only that, like the weather, or it could be how far away you are, or it could be, you know, how hot is it outside, or it could be like there's an infinite number of variations of the Eiffel Tower that you can think of, right? And so every time you ask it, it's going to do something. It's never going to be the same ever, unless you can describe.
Michael commented stochasticity.
Yeah, exactly. Because
stochasticity is built into DALL-E.
Yeah. You know, but again, if you were trying to, you know, translate the Eiffel Tower in a sentence, well, then it would be very discrete. Or if you're trying to look it up in a dictionary, then it would be very discrete. But again, in terms of what it actually really means relative to another observer, it's infinite.
Yeah, I would say that's a fair point, and it's something I would need to think about a lot more, to think about how that relates to our theory. So you are right that in a sense there is an infinite degree of variation. So just talking about, you use the example of the angle, or how far away you are, or what kind of elevation you have. So those are, of course, continuous phenomena. Distance is continuous, angle is continuous. So in that sense, there are continuous variables where there is an infinite amount of variation. But I would argue that takes us outside the domain of lexicalizable concepts. So I would say that's a task that's beyond the scope of lexical semantics.